Now, when we say typical workloads, what are the workloads that come to your mind? Or what are the workloads that we could call as typical workloads? I think if you're thinking of IO, then I'm sure that you're already thinking of either the sequential IO or the random IO, right? This both could be called as typical workload. Either all the IOs are sequential or all your IOs are random. And we can measure performance with both of these, like if all the IOs are sequential, how rate technique 1 versus rate technique 2 versus rate technique 3, so on too. Versus if all the IOs of the workload is random IO, then how does it do? And again, in each of these, sequential and random, we have both read and write. And same for even this as well. So sequential read, sequential write, random read, random write. That's how we would evaluate all our rate techniques that we discussed here. Okay, so enough about why we need rate, what is rate, what are different components of rate, how do we evaluate rate, what is important when we talk about rate to talk about. Enough about all this. Now let's get to the point of exactly what are these rate algorithms. So what are the rate algorithms that we are going to design, that we are going to discuss, or what are the rate designs that we are going to discuss? Today we are going to discuss some of the most popular rate designs, such as rate 0, also called as striping, rate 1, also called as mirroring, rate 4, and we'll touch to rate 5. Rate 4 and 5 are very similar to each other, you'll see so. But most popularly, we use rate 5 today, which because it's similar, very similar to rate 4, it has almost overtaken over rate 4. So, but to understand rate 5, it's first important to understand rate 4. And these both are parity-based redundancy. So these are the rate designs that we'll be discussing. Let's start with the rate 0. Well, rate 0, I would say, is not really a rate because it does not do any redundancy inside it. A rate stands for redundant area of inexpensive or independent disk, right? Inexpensive, as we just talked about in the beginning, could be debatable. So we can replace that I with independent disk. But coming back to rate 0, because it does not perform any redundancy as it's in the R of the rate, it is not actually a rate, but well, it gives an excellent upper bound on performance and capacity. Thus, it is worth studying about it, or it is worth understanding rate 0. So why do we have rate 0? Or why are we discussing about rate 0? Is because it's an excellent, it provides excellent upper bound on, we discussed 3 metric, right? Performance, reliability, and think of it, capacity. Excellent upper bound on performance and capacity. And we cannot say reliability because rate 0 doesn't have any redundancy. So what does rate 0 do? As it's also called striping. So if we have 3 disks, disk 0, disk 1, disk 2, disk 3. So if we have 4 disks from 0 to 3, that's 4. Then if we are implementing rate 0, if the order in which it would store blocks is block 0, 1, 2, 3. So it would stripe each individual block across all these 4 disks. And then again, when we get block 4, then it would store on disk 0, block 5 on 1, 6 on 2, 7 on 3, something like this. So all the blocks are spreaded in round robin fashion. Here, stripe, it's blocks in the same row. So what is advantage of doing something like this? Or why would we want to do something like this? That right, if you have 4 disks, you might as well fill the whole disk 0, then go to this disk 1, then go to disk 2, and then go to disk 3. Rather than doing something like this, what is an advantage of striping all our blocks, all the incoming blocks across all those 4 disks at once? Any thoughts on advantage? Think. Well, if you are thinking of parallelism, then you're exactly correct. So it helps us to extract the most parallelism. From the array. When requests are made for contiguous chunks. For example, a large sequential read. So let's say if we got a large sequential read that is for block 0, 1, 2, and 3, then we would be able to utilize all these 4 disks, rather than if we would have gone about if we would have done it the other way, where we would have filled whole this 0, then this 1, then this 2, and then this 3, then this sequential IO of reading blocks 0 to 3 need to be served, all of them. If blocks 0, 1, 2, 3 are stored on just 1 disk, then it needs to be served by just 1 disk rather than 4 disks now. So more the merrier, right? The more parallel it is, the better we would be able to, faster we would be able to do. So if it would have taken a single disk, would have taken certain amount of time, but now we have more disks, so we expect it will take, it may take lesser than what a single disk would take to do entire job all by itself. Now this job is divided among different disks. Do we have any other benefits? Okay, if you can't think of that, maybe probably not. But then there is another thing that we mentioned over here, which is contiguous chunk. And if we focus on chunk, then definitely another terminology that comes to my mind is chunk size. Chunk size is basically just how big this chunk is. Now, does the chunk size matter? Like how large, like until when we could extract the benefit of this parallelism? And for what size of IO, does that matter? Yes, it does. But why does the chunk size matter? because chunk size affects performance of the array. Now, let's say, for example, small chunk. What would it mean? It means many files get striped across many disks. Thus, it would increase our read-write speed of the file. But here now we have to do the positioning to find where exactly this block in any particular disk is the one that we need for this chunk. So it will lead to the positioning overhead. What are the positioning overhead in hard disk that we talked about? Seek and rotation. And this are definitely not something that we could neglect, right? The positioning, accounting for positioning time is important. So, but positioning time of entire request is determined by maximum of the positioning time of request across all drives. So as we always say in systems, the devil is in the details. It looks a very simplistic mechanism, right? Well, you have a piece of data, just chop, 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 and distribute that across all the disks that we have. But still analyzing that or taking a closer look at that, we get to know so many pros and cons, or so many different aspects of how we can take the best out of this mechanism. This determining the best chunk size. Now it's correct. It's like something's looking wrong with that spelling. Is hard. Now, assume that we have single block of 4 KB, and you could think of what would happen in this scenario, depend with the variance of chunk size. If you have, depending on number of disks that you have in your RAID, how would you align that? And which would be good, which may be not good. Again, that relation depends upon how much time, how much positioning time are we spending while we seek for or while we rotate to get the piece that is being allocated to each individual drive. So if we know all these parameters in advance, then maybe we could come up with this best chunk size, but determining all these parameters, exact parameters in advance is tough. So definitely it's challenging to determine the best chunk size, and it may not be the same as time proceeds or as workload change. So back to the RAID 0 analysis. Now, if we put RAID 0 on the 3 axes that we discussed earlier. In terms of capacity, how is RAID 0 doing? Excellent, right? Because we have n into b, whatever n is number of disks, b is number of blocks on each disk. If we have n disks, each with block b, then we are able to utilize whole n multiplied by b, that capacity. So it's doing excellent. In terms of reliability, terrible, because there is no redundancy. So if we lose the data on any one of these disks, it's lost. Don't even ask where it went. We have no mechanism to recover because we didn't prepare for that. In terms of performance, well, this depends. So good as all this are utilized, right? Now, if we would have concentrated our workload just on a single disk, then we are just using that one disk. But now here we are utilizing all the disk for any workload rather than directing all the workload to just one disk and 3 other disks being idle. So it improves the utilization. Good as all the disks are utilized. And often in parallel. Now, if they're utilized always in parallel, we cannot say that. It depends on workload. So often in parallel to service users' requests. So this is how RAID 0 could be put into our 3-axis or metric of concern. Now, if we want to evaluate the performance, as we talked about earlier, that it's a bit challenging because we need to have an idea about the workload to evaluate the performance. So can we take a closer look in evaluating the performance for RAID 0 further? First, let's take what are the metrics that matters to us in terms of performance, latency and throughput. So first, if you want to evaluate performance, then we want to talk about single request latencies, which is how much parallelism can exist during a single logical I/O operation. Because if we have a request that's of size X, but now we can chop this size X into 4 equal parts, and we could compute or we could process all these 4 equal parts, serve all these 4 equal parts, because we're talking about the IO, not about the CPU, in parallel. So the total time that we would take is exactly the time that we would take to process X by 4, right? So that's the single request latency in this case. Second, steady state throughput. Which is total bandwidth of many concurrent requests. So these are the 2 important parameters that we want to talk about when we talk about performance. Now, as we already talked about, that we would have to stick with some well-known workloads, and only then we can make sense out of comparing performance across different RAID algorithms. And 2 of our most favorite workloads of all time are 100% sequential and 100% random. So 100% sequential, what is this workload